So, for a few lectures now, I promised that no longer would the clouds open up and Professor Landon's face pop through and say, "Here is the value of h you should use for this problem." And then the clouds would close back up. Right now, in this very lecture, with bated breath, we'll say, you'll be able to find your own h. Not for all cases, but for flow inside of cylindrical pipes. And, this obviously isn't all possible h's in all possible cases, but there are plenty of examples where we have flow in cylindrical pipes, whether they're blood vessels or the pipes under my house or anything else. Flow through cylindrical pipes. There are plenty of flow through cylindrical pipes in bioengineering, and it would be nice if we could find our own h for them, because relying on a million individual experiments to figure out the individual h for your individual system would be cumbersome, right? So it'd be nice for us to have the ability to compute our own h for this very common flow. So last time we talked about this h could basically be a function of a ton of variables, and we did an h bar because we were dealing with an averaged we were averaging over the pipe length. We said h bar could be a function of a ton of variables, and in particular it could be a function of the pipe diameter, the pipe length, the fluid density, the fluid specific heat, the fluid's thermal conductivity, the fluid's viscosity, as well as the fluid's average velocity in the pipe. So this is a ton of variables, and we said, hey, wait a second, we're not actually going to do it this way. We're going to do it instead by saying that h bar times the pipe diameter divided by the thermal conductivity of the fluid is going to be a function of three non-dimensional groups: the length over the diameter, the Reynolds number, which is density times average velocity times pipe diameter divided by fluid viscosity, and the Prandtl number, which is mu times Cp, specific heat, over the fluid's thermal conductivity. So rather than having one function of 7 variables, we have a ratio as a function of 3 other ratios. And this non-dimensionalization proved to be very useful because, for experimentalists, it basically cut down on the amount of work that they needed to do. And we basically said, hey, hypothetically, there's one function, one ring to rule them all. No, one function to rule them all. Hypothetically, there is one function that could rule them all for all of these cases, but it turns out that, hypothetically, there's a single function. So hypothetically, there's a single function. In reality, it's actually useful to break up this function into a couple specific cases or a couple specific domains. So in reality, we'll break it up in reality, we'll break it up into the most common scenarios. For example, hypothetically, there's one function that describes this relationship, but in reality, it's easier to deal with one function that deals with laminar flow and one function that deals with turbulent flow, so we'll have 2 separate simple functions rather than one complicated function to try to bring it all together. And then there are a couple other criteria that will break it up. So in reality, we'll break it up with the most common scenarios. So where are we going? We want to be able to find our own h. So one of the first things that we're going to do is we're going to build a chart with these functions. Right, so we're going to break it up into these simple functions with the criteria for their use. Essentially, like, what range of Reynolds numbers is it appropriate to use this simple function? What range of Reynolds numbers is it appropriate to use this other function, right? So this is basically going to going to do this. So we'll build the chart, and in building it, I'll describe basically how you can use it to pick the right formula for the right H for your problem. And it turns out that one of the elements within this chart is the entrance length negligible. So I'm basically going to build the chart with entrance length as part of it, and I'm going to leave exactly how you can use that criterion. What is the entrance length? I'll elaborate on that later. So first we'll build the chart. Entrance length will sort of be one of the questions in the chart. You won't be able to answer that quite yet until we get to the second part of the lecture, which is basically what is the entrance length? And what are some formulas? What are some formulas for use? So that's where we're headed. So hypothetically, we said there's one function to rule them all, but instead what we're going to do is break it up by 3 questions. And if you answer me these questions 3, I'll tell you which Nusselt number formula to use, which formula to use here. So what are the 3 questions that you need to ask yourself? Question number 1 is, what is the surface heating of the pipe? And this goes back to a couple lectures ago. Remember, we said there were basically 2 very common surface temperatures. One is a constant surface temperature of the pipe, and then the other was a constant heat flux in the pipe. So a constant surface heat flux. So constant surface temperature is, let's say I have some temperature controller that prescribes the temperature of my pipe, and then the other one is, what is I've basically wrapped the pipe in some heater that basically puts a certain watts per meter squared into the pipe, and that's what we have here, right? So this scenario here, I have some constant surface temperature where I basically prescribed, I have like a whole bunch of heaters and a whole bunch of temperature sensors, and I basically make the whole surface of my pipe some constant surface temperature. This constant surface heat flux is basically, I have the pipe right here, and I'm putting the same number of watts per meter squared through every square inch of that pipe. So, this is a scenario where basically the fluid temperature keeps rising and rising and rising and rising roughly linearly, whereas this is a case where the fluid temperature kind of starts off, its temperature increases pretty rapidly, and then kind of exponentially approaches the surface temperature of the pipe. So it turns out that the H that you get for each of these scenarios is a little bit different. So the first question you need to ask yourself when you're trying to figure out H is, which of these heating conditions do you have on the surface? The second question you need to ask yourself is, can I neglect the entrance length? And I'm going to clarify exactly later in the lecture what does this entrance length mean, but it's basically like, is your pipe kind of short and stubby, or is your pipe long and thin? And if your pipe is long and thin, then you basically have some kind of goofy stuff happening right at the beginning of the pipe, but for the most part, your pipe is what's called well developed. Whereas if your whole pipe is short, then you really need to account for this sort of entrance effect for the fluid just coming into the pipe. If the fluid's just coming into the pipe and your pipe is, if you basically don't give the fluid a chance to kind of fully develop by the time it gets to the end of the pipe, then these entrance effects are going to be important. And I'll clarify exactly later in the lecture, what I mean by these entrance effects, and I'll give some quantitative formulas for you to be able to quantitatively answer this question: can I neglect entrance length? And then the third question we need to ask ourselves is the flow laminar or turbulent? You can imagine turbulent flow, all of that fluid is swirling and mixing, right? Laminar flow, we basically have all of these straight streamlines. Turbulent flow, we have all of this chaotic mixing. Turbulent flow with all of its mixing is going to result in a heck of a different H than laminar flow. So laminar and turbulent flow matters a lot in terms of what the form of this function looks like. And basically they're so different from one another that it turns out to just be easier to separate them out into two separate regimes with two separate functions, one that fits laminar flow well and one that fits turbulent flow well. So when I think about these three questions, I can basically formulate a chart where the columns of the chart are going to be answers to these questions, and then the very final column of the chart is going to be what formula fits best on the answers to these three questions that we give. So let's go ahead and form that chart. Okay, so let's build ourselves a chart. So our first column is basically going to be the answer to the first question, which is what is the surface condition? For example, constant surface temperature or constant surface heat flux. The second question we're going to answer is, can we neglect entrance length? And in particular, can we neglect the thermal entrance length? And then the final question that we need to ask ourselves is the flow laminar or turbulent? And you remember it's laminar if the Reynolds number is less than 2100, and turbulent if the Reynolds number is greater than 4000. And then the final question is basically our function for Nusselt number. And in particular, it's a Nusselt. The D basically says it's a Nusselt number based on diameter, and the bar across the top says it's the average Nusselt number over the whole length of the pipe. And you remember, Nusselt number is h bar times d over k of the fluid, so we can then turn this around pretty easily. And once we use this function to calculate Nusselt number, then after this we can basically say, hey, our h is going to be equal to our Nusselt number times k of the fluid over d. So once we use this function to calculate Nusselt number, that gives us basically all of the information we need to find our own h. And then we can pat ourselves on the back for having found h. Or we can then use this h in whatever heat transfer problem we were trying to solve. So basically, I'm going to give you some functions that's going to give you everything you need to calculate h. So let's go ahead and start filling out this chart. So the first case that we're going to look at is a case where we have a constant surface temperature, and we can neglect thermal entrance length. So this basically means we have a very long pipe compared to the fraction of that pipe that we're having weird entrance effects. And we have laminar flow in the pipe. So this is actually a pretty common scenario in a lot of heat transfer cases. And in this case, instead of actually having a very messy function for Nusselt number, right? Remember we said Nusselt number, right? This Nusselt number could be a function of L over D, Reynolds number, and Prandtl number. It turns out that in this specific scenario, it actually isn't a particularly messy function at all. You ready for it? Nusselt number in this scenario is just equal to 3.66. It's a number. It's not even a messy function at all. It's just a single number. So in this case, if you have these three scenarios, if these three criteria met, you just put 3.66 in for your Nusselt number, plug in your K and D, boom, there's your H. Easy as pie. So there it is right there. Now you may say, hey, Professor Lannon, what happens if we have what happens if we have a case where we can't neglect the thermal entrance length, but we sort of have the same other two criteria as well? Well, I got you covered. So let's say we have a constant surface temperature, but in this case we can't neglect the thermal entrance length, but we still have laminar flow. And in this case, we also have a Prandtl number of of greater than 5. So if we have this particular scenario right here, laminar and a Prandtl number of greater than 0.5. This is just so laminar is laminar or turbulent, but we just have an extra criterion for Prandtl number right here. It turns out that it is equal to 3.66, similar to this, plus essentially a correction factor to account for the thermal entrance length. So in this case, it's 3.66 plus 0.0668 times d over L times Reynolds number sub d times Prandtl number divided by 1 plus 0.04 times d over L to the d over L times Reynolds number sub d times Prandtl number, and this quantity in brackets here to the 2/3 power. So what does it mean? Basically, if your d over L is really, really small, then this term basically goes away in the denominator, and your numerator goes away too. So if your d over L is really, really small, well, that basically means you have a really long tube compared to your entrance length, right? If you have your d over L is really small, that means your tube diameter is really small compared to its length. That basically means that your tube is so long that your thermal entrance length is going to be small. If your thermal entrance length is going to be small, basically this second term essentially disappears and you get this first result back. So you can think of the second term as basically a correction factor that accounts for a non-negligible thermal entrance length. But if you ever had the question, is thermal entrance length negligible or not, you could use this formula, and if it happened to be negligible, you would just end up recovering the same quantity as if it were negligible. You might be like, hey, Professor Lannon, you're sure talking about these constant surface temperature cases all the time. What happens if we have a constant surface heat flux case? And if you have a constant surface heat flux case where you can neglect the thermal entrance length and the flow is laminar, well, it turns out you get a formula for that. The formula for that ends up being Nusselt number is equal to, ready for it? 4.36. Sorry, that's a 4. I'll write it over again. 4.36. Cool. Wow, great. So if constant surface temperature, your Nusselt number is 3.66. If constant surface heat flux, your Nusselt number is 4.36. If the entrance length is negligible and the flow is laminar. For the constant surface temperature case, we have a formula where there's a cool correction factor if the thermal entrance length isn't negligible. There might be one for constant surface heat flux, but I've decided to not include it in this lecture. Now you might be saying, hey, wait a second, Professor Lannon, you've sure talked about all of these cases for laminar flow. Is there going to be one where there's turbulent flow? And in this case, yes, there is one, but it only really works if the flow is very turbulent. For example, if the Reynolds number is greater than 10,000. So if the Reynolds number is greater than 10,000, this works. And there's also a restriction on Prandtl number. Prandtl number needs to be greater than 0.7, but also less than 160. So some restrictions on the use of this one. And it turns out that this formula actually works for either constant surface heat flux or constant surface temperature. So that's pretty nice. And it's restricted in some sense to its thermal entrance length, not explicitly in terms of its thermal entrance length, which we'll talk about later, but restricted to L over D being greater than 10. So basically, the tube needs to be 10 times as long as its diameter in order for this equation to apply. And so what is the formula? The formula isn't quite as simple as one of these constants, but it's still not too bad. It's 0.023 times Reynolds number sub d to the 4/5 power times Prandtl number to the little n, where n could basically be one of two things. 0.4 if the fluid is heating, and 0.3 for cooling. And what is the physics of this 0.4 versus 0.3? Beyond the scope of what we can talk about right now. So, does this cover all possible cases of the inputs to this function? No, right? There are holes, right? That we don't have something for Reynolds number in between 2100 and 10,000, nor do we have things outside of the range of some of these Prandtl numbers, nor do we have ones for cases where, in some cases where we have some heating besides constant surface heat flux or constant surface temperature. So this is an incomplete chart, but I think it's going to be complete enough for you to be able to solve the overwhelming majority of problems you might encounter in heat transfer for bioengineering. So hopefully this chart provides some help. A couple of caveats, right? So what might be some caveats to the use, or some trickiness to the use of this function? Well, here I'm talking about things like fluid conductivity. We talked about things like fluid thermal conductivity, specific heat, viscosity, and density. So strictly speaking, all of these can vary with temperature. So, so here I kind of described these things all as constants, but in real life we know that these things vary with temperature, right? We know that a lot of times, like oils and other fluids, get less viscous as you heat them up. A lot of fluids tend to get increased thermal conductivity when you heat them up because they're basically their electrons are freer, so they can transfer energy to each other. We all know that fluid density changes, right? Hot air rises, all that stuff, right? So all of these properties vary with temperature. So you might be like, hey, wait a second. If all these properties are varying with temperature, but down here I'm treating them all like constants, how is that going to play out? So all of this engineering stuff are approximations anyway. So these approximations are most accurate when fluid properties are evaluated at your mean mixed temperature, right? So strictly speaking, we know that maybe the fluid here close to the edge is different from the fluid at the center, is different from the fluid upstream and downstream. So if you basically said, hey, I'm going to use the mean mixed temperature, and I'm going to use the mean mixed temperature somewhere in between my inlet and my outlet. If you can sort of use averages of averages in terms of what your expected temperatures are, then that will give you and you can evaluate fluid temperatures at that sort of average temperature. Yeah, some parts of your flow might be up a little bit, some parts of your flow might be down a little bit, but if you use the sort of average of all temperatures, then you're going to, and you evaluate the fluid properties at that average of all temperatures, then anywhere in your flow isn't going to deviate too much from what it is. Again, and these are all approximations anyway. Here I've given you four equations which are going to cover a lot of your flows. If you ever encounter a flow that isn't one of these, or you want some formulas that are more complicated but perhaps a little bit more accurate than some of these approximations right here, see chapter 8 of Encropera and DeWitt's. Heat transfer text. So they have some formulas in there for more special cases or sort of extensions of what we have here. And then for non-circular, geometries, right? Here we basically said, we're doing flow in cylindrical pipes, but maybe you might be caring about how air flows through like a rectangular duct for like the heating vents in your house. Or maybe you're like a microfluidics person and you're saying, hey, I have rectangular cross-section channels in a microfluidic device. How is heat transfer going to happen in one of those? For those non-circular geometries, you might need to do computational simulations. Oh, I said chapter 8 of Incompare and DeWitt's text. Also chapter 8 of Rosilli and Diller. Biofluid text. Has a lot of correlations as well. So, so this works, right? This chart isn't going to cover everything. There's some other places where you can find perhaps some cases where these aren't, or you might be able to just search things like Google Scholar. People might publish correlations for functions in special cases that might apply to your system. All right, so let's go back to this question here. Can we neglect the thermal entrance length, right? So can we go back? Let's talk a little bit about thermal entrance length, and then I'll give you a couple formulas for entrance length, both thermal and hydrodynamic, so you can basically compute an entrance length and then compare it to the actual length L, right? So this will basically say, hey, is my entrance length going to be less than, or is my entrance length less than the actual length of the pipe? Is my thermal entrance length less than the length of the pipe? And if both of these are true, then that basically informs using some of the simpler formulas in this chart. So let's make a distinction between two entrance lengths. The first entrance length that I'm going to talk about, is the hydrodynamic. The hydrodynamic entrance length, which I'll give L sub E, and the second one is the thermal entrance length, which I'll give L sub E T. So there are two different sort of physical phenomena or physical quantities. So I'll discuss the hydrodynamic one first. So you can think of the hydrodynamic entrance length as the distance it takes for the flow, i.e. velocity profile, to become fully developed. And what do I mean by fully developed? I basically mean no longer changing with position. So let's sketch out what I mean by that. So imagine I'm looking at the cross section of a pipe. Here's the walls of the pipe. A lot of times when fluid enters a pipe, it might enter with like a roughly uniform velocity profile. And if this flow enters with a uniform velocity profile, well, this fluid is kind of screaming along at some velocity here, then all of a sudden it encounters the wall at the pipe. And we know that flow that encounters the wall of a pipe, the molecules immediately adjacent to the wall, if the wall's not moving, those molecules are also not moving, right? So we know that eventually, some distance downstream, we end up with this parabolic velocity profile, if laminar, right? So parabolic. So that we end up with a parabolic velocity profile if it's laminar. And if we think about it, in the middle, the fluid is actually sped up a little bit, and at the edges, it's slowed down a lot, right? Compared to its originally uniform counterpart. So what's going on there? There's basically this this scenario where the fluid immediately next to the edge stops, and then this effect of the edge kind of creeps towards the center. So basically the slowing downedness of the walls eventually creeps towards the center, and you can imagine it kind of creeps in from both sides and eventually overlaps to basically where this edge effect merges, and then once it merges, essentially the flow becomes fully developed. So what do I mean by here? Basically, once these edge effects have merged, I get my, let's say, parabolic velocity profile if I'm laminar, and then at every point down from the flow, it's the same velocity profile here, 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 here. But between this uniform flow at the inlet and this parabolic velocity profile later on, I have some messiness going on. So what does it look like? Well, at some intermediate region here, I basically have this transition from no velocity at the edge up to some uniform velocity in the center. And a uniform velocity in the center then transitions back to a kind of curved velocity profile to the edge. So there's this kind of region here where there's a sort of uniform core that hasn't kind of been rounded out by the creeping in effect from the edge, but but eventually some distance down the pipe it will. So we might call this sort of creeping in stuff, we might call this something like a boundary layer. And boundary layers, you almost always grow, as you go downstream in the flow. And in this pipe case, they basically grow and merge. And once they've fully merged, the flow becomes fully developed. And we would basically call the distance between the entrance of the pipe and the place where they fully merge, we would call this the hydrodynamic entrance length, or LE. So you can imagine, for some pipes, this effect, this region might be very small compared to the overall length. For some pipes, the pipe may actually be so short that the flow never gets fully developed by the time it exits out of the outlet. And this effect basically depends on the hydrodynamics of the flow going through it. So it turns out that this entrance length is basically a function of the characteristics of the flow as well as some fluid properties. So entrance length is basically a function of fluid density, average velocity, the diameter of the tube, as well as the fluid viscosity, right? You can imagine if the fluid is more viscous, this boundary layer effect is, the edge effect is going to be able to creep more rapidly into the flow, right? Viscous basically means like if these guys aren't moving, their neighbors aren't going to be moving as well. So viscous effects tends to sort of creep it in, which you can imagine if the fluid has a high velocity, basically it blows in there with so much momentum that it takes a while, it takes a pretty long distance for that edge effect to creep in, right? So these effects kind of counteract one another. If the pipe diameter is large, it takes more distance for that boundary layer to creep all the way into the center. And if the fluid has a lot of density, it takes sort of more distance before that fluid gets halted down, right? If a big rig truck has a lot more stopping distance than a golf cart, something like that, right? So these massive fluids with a lot of mass have a lot of inertia and basically have long entrance lengths. So this entrance length is kind of a function of all of these things. It turns out that this, precisely how this function formulates out is interesting, but in a similar spirit to what we talked about with Nusselt numbers and non-dimensionalization, it turns out you can non-dimensionalize this relationship where you basically say your entrance length divided by your tube diameter is a function of Reynolds number. So you could do all the non-dimensionalization steps, and I think that's actually one of the homeworks that you're going to do. You could use Ibsen's method with this set of variables, and you could churn out what this that this relationship exists. It turns out that in a similar spirit to this chart here, where there are a whole bunch of different conditions, rather than having one function to rule them all, it's easier to have two separate functions. If your flow is laminar, then this entrance length divided by diameter is 0.0567 times Reynolds number. And if the flow is turbulent, then it's 10. That's it. 10. Pretty straightforward as far as functions go. So basically, these two relationships give you, having these two relationships basically give you the information you need to calculate the entrance length. And then once you've calculated the entrance length, that tells you whether you can neglect it or not, and basically which function you should be using in your Nusselt number computation. And then once you have a Nusselt number, you can of course find h. But this chart was basically saying, hey, can we neglect entrance length? And for this chart, it's actually most important whether you can neglect the thermal entrance length. So here we haven't really talked about heat transfer at all. This is essentially just describing the hydrodynamics. Now, of course, we know that the hydrodynamics are important for heat transfer, but we should probably talk about thermal entrance length so you can actually answer the question on this chart. So thermal entrance length. First I'll tell you what it isn't, and then I'll tell you what it is. So it's not the distance. It's not a distance after which temperature becomes constant. So it's not a distance after and I can't put enough exclamation points after this, right? So thermal entrance length is not a distance after which the fluid temperature sort of becomes constant, sort of equilibrates with the pipe temperature or something like that. It's what it is basically a distance after which we don't get some added effect from the hydrodynamics. So it is a distance So it's basically a distance after which we no longer get an added effect from hydrodynamic, and essentially it is a distance it's basically a distance after which h equals constant. So it's not a distance after which the fluid temperature is constant, it's a distance after which h essentially becomes constant. And that's kind of reflected with this sort of thing here, right? Where basically if your entrance length is negligible, then your Nusselt number is basically a constant, which basically means your h is a constant, no longer dependent on what position we are downstream in the pipe. So, so what does thermal entrance length look like? I'll kind of sketch it out here. So imagine my fluid comes in with, let's say, some small uniform temperature. In this case, so basically I'm plotting temperature as a function of radial position here. So the fluid, let's say, comes in at some uniform low temperature. There's basically this thermal boundary layer. Which isn't necessarily where the surface temperature of the plate has kind of fully penetrated into the flow, but it's basically an effect of which the fluid that isn't within a thermal boundary layer is basically completely at the original T sub r. So in this case, this fluid is at this fluid is basically at the original inlet temp. And then the fluid transitions from your original inlet temp up to your TS right here, let's say. And then downstream, from here, you basically, so within this region that's not affected by the thermal boundary layer, you get your original surface temp. Here, you haven't fully reached your surface temperature with everything. It's just finally when you're past your thermal entrance length, the fluid at the middle at least has had some effect from your temperature from your edge. And then later on, you still have some deviation, right? You still have heat flowing in from the outside. It's just that every part of the fluid is now somewhat affected by your edge temperature, something like that, right? So here's your, you basically have these thermal boundary layers that are growing in from the edge. It's not that all of the fluid has entirely reached the surface temperature by the time you're past the thermal entrance length. It's just that some point in the fluid has. And, your fluid core temperature still might have a ways to go to get up to the surface temperature. It's just not that it's just at a point where it's now not completely unaffected by it. You might be saying, hey, Landon, could you give me some function, right? Last time, for hydrodynamics, you said, hey, we have this function here. So what might that look like for thermal entrance length? Well, basically the thermal entrance length equals a function of a couple of variables. It's, understandably a function of the same variables as the hydrodynamic entrance length, plus a couple additional properties to account for the fluid thermal properties. For example, the fluid's thermal conductivity and its specific heat as well. You do a non-dimensionalization process like we did for Nusselt number, etc., and it basically says that your thermal entrance length as normalized by your pipe diameter is equal to a function of Reynolds number and Prandtl number. It's a function of Reynolds number and Prandtl number. So what might this function looks like? Well, we basically break it up into two separate scenarios. 0.0567 times Reynolds number, and this looks pretty familiar, not just times Reynolds number, but for the thermal entrance length, but also times Prandtl number. So it's basically the same as your hydrodynamic entrance length, except for this additional factor of Prandtl number. So your thermal entrance length is basically this right here if your flow is laminar, and then if turbulent, 10. There it is, right? So there we have it. So this is what's going on here, right? So so what would you do if you wanted to find your own H? Well, you would answer, hey, what is my surface condition? Constant surface temperature, or constant surface heat flux. That might inform which one you do here. You then say, hey, can we neglect the thermal entrance length? Well, in order to do that, you need to calculate what the thermal entrance length is. And you can basically say, you can look at two cases. Is the flow laminar or turbulent? Well, to do that, you basically calculate Reynolds number first and then compare it to your 2100 or 4000. That basically tells you, which of these equations to use for thermal entrance length. You calculate your thermal entrance length. That allows you to answer this question. Then at that point, you'll have already answered the question of whether the flow is laminar or turbulent. And that can basically tell you which thing to use here. Hopefully you find an equation where where one of these equations in this chart applies, and if not, then you'll basically need to look for other resources to answer that question. And all of this is to find Nusselt number, Once you find Nusselt number, you can plug it in here, plug in your K and D for your fluid. That gives you all the information you need to find H, and hopefully that H was something, some key piece of the puzzle for the heat transfer problem that you were looking to solve for flow through pipes. All right, so thanks for your attention. Good luck with your study of heat transfer, and take care. Cheers.